Okay, so our next speaker is Varun, and he will be speaking on randomization of polynomial factorization.
Okay, thank you, Varun, for the introduction. So yeah, last time I had a similar talk. This time we made a little more progress towards the randomization of polynomial factorization. It's I guess I didn't really time it well. It's a heavy bunch of slides, but feel free to stop me at any time. And if I feel like I'm short on time, I'll sort of skip and summarize things. So so the main so the main characters of this talk are going to be arithmetic circuits and their properties, polynomial identity testing, something called the resultant and pseudo resultants, which are things that help you check GCD conditions. Then there's Newton iteration, which some of you might have seen in calculus and so on. And then just good old linear systems. And I won't go into a lot of detail about everything, but mostly these are the things that show. And the field that we are going to be working over is rational numbers. Now we're talking about polynomial factorization. So let's start with univariate. Does anyone know? Can we factorize univariate polynomials efficiently? Well, over reals and so on, there's all sorts of Abel-Ruffini theorem and things which tell you these are hard problems. But over rational numbers, we know that Loas, Lenstra, and Lenstra, they gave us efficient algorithms to factorize polynomials over rational numbers, univariate. Now, what about multivariate? Before we go into details, we should be clear about the way we are representing polynomials in all these questions. And the model of choice is going to be arithmetic circuits. Let's say this is the polynomial. One way of computing this is using an arithmetic circuit that looks like this. It's just like Boolean circuits, but your nodes are now product and sum nodes, and your leaves are variables, and you do the operations naturally, bottom up. Now, in general, when it's a directed acyclic graph, we call it circuits. And if it's a tree, if the underlying graph is a tree, you call it a formula. The parameters of interest are going to be the size of the circuit or formula, which in general is, let's say, the number of wires. But if it's a tree, you might as well use the number of leaves as the size of the formula. And another important parameter for us will be the depth of the circuit, which is essentially the longest path from a leaf node to the root. All right, and what is the result that I'll be talking about? So fix any two constants, delta 1, delta 2, natural numbers. We give an algorithm which runs in sub-exponential time. Sub-exponential seems bad, but in the kind of questions we are working with, we don't know how to do better than this. Your input for this algorithm is some polynomial which is computed by a depth delta 1 circuit of some low size. So constant depth circuit, and the output will be a list of circuits such that if some polynomial divides your input polynomial and it has a low depth circuit, then it will feature in this list. All right. So any low depth circuit which divides the input polynomial is going to be in this list, but there are some issues. The circuits in L might not be very nice. In the end, if there's time, I'll tell you what it means that the circuits aren't very nice. Plus, the output list might also contain things that do not correspond to actual factors. So this is, if you're familiar with coding theory, it's almost like a list decoding sort of a statement. All right.
So what in the circuit model, when the LLM thing is not quite clear, it's like it's very construct like in login depth and login size, they can construct a dpn for long. The LLM method needs the coefficients. So is that this problem in this form, but it's not clear that LLM implies that you can solve even for univariates in this setting.
For univariates in this setting, so what's the
for univariates you shouldn't think of the circuit model.
Yes, univariates
to become harder.
Yeah, that's what.
So for LLM, you need the polynomial list of coefficients.
Yeah. So but even if I look at this version,
so you're saying you might be able to encode things extremely succinctly.
Yeah, I mean, the simplest case is like I can encode x plus
X to the 2 to the n by n. Sorry. Yeah. Yeah, no, I mean, in general, even when we talk of small circuits, we think of polynomials which have degree, which is polynomial in the number of variables and so on. And again, the
growing, the number of variables is growing.
univariates is not.
Univariates is just not part of.
Yeah. But it will be a subroutine that's used.
But the subroutine will be other.
The subroutine will
So we'll all the coefficient.
Yeah, yeah. Okay. I hope the main statement is clear. All those delta 1, delta 2 are constant. So for any set of these sort of constants, you get a separate algorithm. And I said these have to be constant depth circuits. To figure out why constant depth is important, I'll quickly talk about what is this problem of polynomial identity testing. Here your input is some polynomial, multivariate, which is given to you either as a black box circuit, which means you are allowed to evaluate the polynomial over elements from the underlying like q to the m or something. Or you might be given white box access, which means you can see the innards of the circuit. And the output that we want is, we just want to know, is this polynomial just the zero polynomial or is it actually some non-trivial polynomial? If you're just given the monomial representation, this is easy. If there's any monomial, it's a non-zero polynomial. Algorithm, which you also sort of saw in Renald's talk, which is just evaluate the circuit on sufficiently many random points. By the Schwarz-Zippel lemma, this will, if the polynomial is non-zero, you will get a non-zero evaluation. But what about deterministic algorithms? So let's talk about the black box setting where you're allowed to do evaluations. And if you're talking about getting black box PID algorithms for a certain class of polynomials, this is essentially the same as constructing hitting sets for that class of polynomials. A hitting set is just given this class of polynomials, you want to construct a set so that for any non-zero polynomial in that class, there is some point in this hitting set where the polynomial evaluates to non-zero. So in some sense, it's a small set of points that certify the non-zero-ness of polynomials in C. Right? And the reason we want constant depth circuits, I'll use this very familiar notation AC0, which is also used in Boolean circuits, for constant depth arithmetic circuits. Why do we care about these? So a recent breakthrough by Newton Limai, Shrikant Srinivasan, and Sebastian Tavenas gave us super polynomial lower bounds against constant depth circuits, which means Chau-Kumar-Solomon, which tell us that these sort of bounds give you small deterministic hitting sets. And in particular, the kind of lower bounds that we got from LST, they give you sub-exponential size hitting sets for constant depth circuits. So this is essentially where the sub-exponential running time for our algorithm comes from. Okay, so now what do we know about multivariate polynomial factorization? A very, very quick overview. So from a long line of work by Kaltofen, Trager, Gathen, we have polytime randomized algorithms for computing factors of polynomials that are themselves computed by small circuits. And those factors that are output, they will also be small circuits. And there are a bunch of other results on polynomial factorization depending on the specific settings you're looking at. You can refer to a survey of Saraf and Shpilka for this. Something of interest to us will be these results by Shpilka, Volkovich, and Kopparty, Saraf and Shpilka, which says that if you can deterministically do PID for small circuits, then you can do polynomial factorization, right? But there's something a little not so nice about this. So the result of Kopparty, Saraf, Shpilka tells us that even if you want to do polynomial factorization for very simple circuits, you might need to do PID for general polynomial size arithmetic circuits. The eventual sort of goal in one goal for this line of work is you want a fine-grained connection like this. If you can do PIT for a specific class C, then you want to be able to do polynomial factorization for the same class C. Any question? These are small steps. Okay.
The small order means the constant depth for them.
No. The result there is small unbounded depth.
Okay. So this is if you're going to get it for polynomial size circuit.
Polynomial size circuit. Yes. But you would like to say this even if C was constant depth circuit, you would potentially like to say something like. So okay, now I'm jumping into the a specific case of the algorithm. So this specific case is that the kind of factors that we are looking for are going to be roots in one special variable. So let's say f of vector x comma y is the polynomial that you're looking at. And I'll assume this is sort of without loss of generality and it helps your algorithm do things a little easily. I'll assume that the polynomial is monic in this variable y, which means that it looks like this. Y to the power capital D plus everything else. So there is no x term that is showing up in the highest degree y. And the kind of factors we care about look like this. F of x comma y is y minus gx times h of x comma y. So what does this mean? It means that gx is a y root of f of x comma y. And I'll also assume that gx is not a y root of h of x comma y. So in some sense it's a multiplicity one root for this polynomial. Is this setting clear? So what's the idea? You are given f of x comma gx. So you are given f of x comma y, and you want to find some g which is a root in the y variable. The idea is that I want to get the coefficients of this polynomial g, one gi at a time. And how do I want to do this? I want to do this iteratively. Given the coefficients to some degree, it turns out that the next coefficient is uniquely determined using a tool we are all quite familiar with, Taylor expansion. If some starting conditions are satisfied, and the whole game is to ensure that we can satisfy these starting conditions, is a high-level idea. Okay. So let's say y minus gx divides fxy. So g is a root, y root of f. And we want to find the G0, G1, G2, so on, step by step. Again, just restating what we have. So what does this mean? So f of x comma that polynomial g of x is 0. In particular, it means if I plug in x is equal to 0, then f of 0 comma y, which is a univariate polynomial, at y is equal to g naught is going to be 0. So g naught is a root of f of 0 comma y, which is a univariate polynomial in y, right? So we can get our hands on this g naught, which is factorize the univariate polynomial f of 0 comma y to get your hands on the.
But this now you need coefficient access.
Now you need coefficient access, and this is why it helps that we are working with small arithmetic circuits, because now you can set the variable, like you set x variables to 0, and then you can interpolate and.
So the algorithms for these things, where typically we assume that the multivariate circuit is constant speed. Constant, meaning I'm not allowed to write arbitrary constants here. Otherwise, the bit complexity can go.
Okay, so we have the constant term of the root that we're trying to find. Now, how do we get the next term? Is the coefficient of the linear term. Okay, also, sometimes I'm using x vector, and right now I just have x. It's easier to think about it in the bivariate case, but these things work out even in the general case. So now I have f of x comma gx. Gx I know is g naught plus everything after that. So g tilde x is going to be the linear term plus the quadratic term and so on. And now I want to use Taylor expansion. In general, the statement for the expansion is something like this. I want to focus on the y variable and expand around some point y is equal to alpha. Then I can write it as f of x comma alpha plus y minus alpha times the derivative with respect to y evaluated at y is equal to alpha and so on. There's a factor, yeah, there's 1 by 2 factorial thing. And here I'm not thinking about convergence or any of those issues. I'm purely looking at these as formal power series. And now instead of y, I'll plug in the root gx again, and then I'll expand it around the point g0. And I'm just opening it out. And this is again the same expression, except g tilde x, I've written it as g1x plus dot 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 and so on. And now what I want to do here is focus on the linear part of the right hand side. Now the whole thing is, this is an infinite summation which is summing up to 0. And the linear parts can only cancel among themselves. So they should sum up to 0. And if you focus on the terms of degree at most 1, then what you'll get is something like this. That g1x is giving you a linear term. Oh, there is a pointer, right? The g1x is giving you a linear term. So you have to take the constant term of this part. This g1x square is already giving you a quadratic term. So nothing is going to show up after that. So I just have g1x times the constant part of this polynomial. And there is something here. We don't quite know what shows up from there as a linear term, so we just let it be. But the point is that you can now write down g1 in terms of the remaining terms. And this is essentially the usual Newton iteration type formula that shows up here. And we need to be a bit careful. So this is what's showing up. Well, we don't want this to be a rational function or something like that. So x should certainly divide the numerator here. And this is some constant, right? We have substituted 0 and g0 here. And does x divide the numerator? It does divide it because of the way we started off this process. We assume that f of 0 comma g0 is 0. We found a point like that. So then f of x comma g0 only has at least linear terms, so it is divisible by x. And so now if we look at the current best estimate for the polynomial we have the constant term, we have the linear term g1x, and if you just multiply x by it, you'll get this g0 minus this term. I guess maybe this is probably the Newton iteration that everyone's.
How do you know the y partial derivative from 0?
Yes, good. So, okay, I'll just get to that in a minute. So in general, this works for every iteration. If you have coefficients till degree I, then you can get the degree I plus 1 coefficient by using the same expression. And the important point is the denominator stays the same. And it is a constant, but we don't know if it's non-zero. So now there are two requirements. This works if you have your hands on a starting point, which is the root, which is this g0. And you should ensure that the denominator is non-zero, right? So this is the polynomial that we started off with. I just want to quickly, what do I want to do, right? I want to know, is this condition holding? Is the partial derivative of f with respect to y at 0 comma g0 not equal to 0? I'm just going to try and figure that out. You apply product rule, differentiate it, and evaluate it at 0 comma g0. And what you get is h of 0 comma g0. H is the quotient of the factor that you were trying to get. Alright? This means that the denominator is non-zero if and only if this quotient evaluated at the same point is non-zero. But it's possible that the quotient evaluated at 0 and g0 is just the g root at 0. It's possible this is 0. But notice that we started off with y minus g of x not being a factor of h of x comma y. It was a multiplicity 1 root in some sense. So we know that h of x comma gx as a polynomial is non-zero. So even if it evaluates to 0 on x being 0, in general it is non-zero, which means that by again short triple lemma and so on, there should be other points A where this denominator can evaluate to non-zero. So the solution is going to be you shift your origin so that now the denominator is non-zero. All right. But wait.
So you said for most tail joints, we will all but finitely very
Okay. Have to use the fitting set. That's right.
So okay, so there is okay. If you are working with bivariate, then this is just a univariate. So this is just the usual number of roots is at most degree sort of statement. And if you are working over, if you're working in multivariate setting, this is generally 2 by Schwarzschild if you're just working with any grid from the underlying field or something. But yeah, in the specific setting, if you want to find the point, you'll have to use a small hitting set that shows up. But this is still not quite good enough for what we want, because not only did we want that this a comma ga should be non-zero for at h, but it should still be a root of the original polynomial. It's possible that the non-zero, that the shift that you find here, it doesn't work to ensure that it's still a zero of the original polynomial.
We should just x. Gx.
If you shift just x.
Oh, because the variable thing. Okay.
Variables are shifting, right?
Not a of g.
Okay. So the usual solution for these sort of problems is using the resultant. I won't go into too much detail. The resultant is basically this. If you have two polynomials h and g, the coefficients can have x variables hiding in them. Then the resultant is some polynomial that is constructed using their coefficients, the coefficients of g and h. There's some determinant that shows up. And the really important fact here for us is that the resultant is 0 as a polynomial if and only if the GCD of g and h is non-trivial. Right? And I'm not sure I have enough time, but I'll rush through a quick and dirty proof. The reason you can connect GCD being non-trivial to some determinant being 0 is because this ends up being a linear system. You want to know if there are these Bezout coefficients which show up in Euclid's algorithm. You want to know if there are Bezout coefficients which give you the combination being 1 for these polynomials, and that's basically a linear system, so a determinant shows. But the important point is this characterization. And why is this important? When we started off with our factor g and the quotient having GCD 1, which means that their resultant is non-zero. So the GCD is trivial, which means the resultant is non-zero, which means that there exists an instantiation of the x variables so that the resultant still stays non-zero, which means that there exists an instantiation so that the GCD, when you set x variables to a, the GCD of the factor and the quotient remains 1. And at this point, we went to not just factors of the form y minus gx. This is true in general. But now if you go back to the setting that we care about, which is your factors were of the form y minus gx, then this just means that y minus ga, because GCD is 1, it means y minus ga does not divide h of a comma y. So h of a comma ga is not equal to 0. But also, y minus, by the way we constructed this, y minus ga is now not a root, but ga is certainly a root, a y root, because y minus ga is inside f. So this gives us what we want. What does this mean? If you want to find such an a, you want to find a vector which ensures that this polynomial, which is some resultant, is non-zero. And the idea here is to use PID. And how do you use PID? It turns out that if the factor you care about is easy here for us means it has a constant depth circuit, and the quotient is also easy. This might not be immediately true, but it turns out that if the factor is easy, then the quotient is also sort of easy. Now, even then, it's not immediately clear that the resultant of these two things will also be easy. If that were true, then we are done. Then you can take a point which maintains that the resultant is non-zero and move ahead with Newton integration. But this is not immediately clear. And what we were able to show is another easy alternative, which we call the pseudo resultant. I'll take 3 or 4 minutes more. And the very high level difference between what the pseudo resultant does as compared to the resultant is that the resultant ensures that once you drop down to the univariate world by setting x variables to something, the factors that came from G and the factors that came from H are still going to have GCD 1. So they are going to have no intersection, and that helped with Newton iteration. But this was a little too strong. What pseudo resultant gives us is that once you go to the univariate world, there might be an intersection between the factors that came from G and the factors that came from H. But the factors of G won't be completely subsumed by the factors of H. There will be some factor here which will not divide H of A comma Y, and then you can use a root for that univariate to start your Newton iteration. Because then H of A comma Y, which is what showed up in the denominator, that will stay non-zero. So that is the place where pseudo resultant shows up, and this is the final sketch of the algorithm. You take a hitting set for constant depth circuits, and then for each point in the hitting set, you do the following. You shift your origin so that now the polynomial is nice. You might have to do a couple of more shifts to ensure that it's monic and so on. But essentially, you want to ensure that you can do Newton iteration. So you use the pseudo resultant to get this point, and then you run Newton iteration. And there is a final cleanup step which doesn't quite show up in the case where the factor you care about is just a root. But in general, you'll have to do some linear system solving thing to get the final circuit for the polynomial, for the factor you care about. And then now you did this for every point in the hitting set. So you output this list of circuits. And this will be a subexponential sized list. So that was the sketch of the algorithm. Just any questions here?
What is the
What is the pseudo resultant? It's I can tell you after the talk. It's a little not that. The expression is clean, but it's not easy to motivate it into. So, okay. Future directions. So, okay, as I said, the circuits that we output from the algorithm, they are not nice, which basically means they have some division gates in them, they can have unbounded depth, and there might be things that don't even correspond to factors. So we'd like to remove these caveats. And we also, so in general, even the existential question of if your polynomial is nice, then are its factors also nice? This is not true when you think about the polynomial having small formulas or small constant depth circuits. It's true because for small polynomial size circuits in general. In fact, you have an algorithm from Kaltofen and so on. But for formulas or constant depth circuits, we don't even know the closure result, which means if a polynomial has a small formula or a constant depth circuit, do its factors also have small formulas or constant depth circuits? Small meaning polynomial size, so on. We don't know this. And similarly, in the setting of sparse polynomials, which means number of monomials is polynomial size. Even there, we don't know, can you get all the sparse factors of sparse polynomials in, let's say, quasi-polynomial time? It's quasi-polynomial would be pretty great. We don't know how to do that now, but we know something, we know a weaker statement like this. We know how to get constant depth. We know how to get constant degree factors of sparse polynomials in quasi-polynomial type. But the hope is you can do this in general for sparse factors. This is the paper. That's all. Any questions?
So earlier you said that nice that circuits are not nice. We are ignoring them. Is that what you mean by not nice?
Yeah, these are the things. These are the issues.
Okay, but now you said that even when they are nice, we do not know some certain things.
No. Oh, okay. Oh, no. I overloaded the term nice here. Here, nice means the circuit being like this. Here, nice means small formulas or constant depth circuits.
The word nice means the word nice.
Nice too many.
Further questions? Okay, yes, thank you, speaker.
Slides merely after the introduce you, right?